Hello there, my name is Professor Karim from University of Science Malaysia. In this presentation, I'm going to discuss about the properties and chemical reactions of fat and oil with a focus, of course, on the palm oil. Understanding chemical reactions of fats and oils is very important when we discuss about the modification of fat to produce high-value products and also to understand the chemical reactions during deep fat frying. Fats and oil contain triacylglycerols, or commonly known as triglycerides. And these triglycerides can undergo chemical reactions such as hydrolysis, oxidation, hydrogenation, polymerization, interesterification, and isomerization. Chemical reactions such as hydrolysis and oxidation, as well as polymerization, can occur during deep fat frying process when we use the edible oil for frying. Reactions such as hydrogenation, interesterification, and isomerization can occur when we do modification of fat and oil. So in the next few slides, we will discuss in more detail each of these chemical reactions. One of the common chemical reactions in fat is hydrolysis or lipolysis. This is basically the hydrolysis or breakdown of the ester bond by the action of enzymes such as lipase, or by the action of heat and moisture, for example in the high temperature frying of oil. And the process of hydrolysis will produce free fatty acid, or FFA. So in this diagram we can see the chemical structure of triglycerides. So this is the ester bond here, and we have the free fatty acid, and by the action of enzyme or by the action of water or heat, the ester bond can be hydrolyzed or be broken down to produce free fatty acid. And if the hydrolysis is carried out to the completion, more ester bond will be hydrolyzed to produce more free fatty acid. Usually in the crude oil, the hydrolysis is not desirable, and we have to minimize it, because when we get more hydrolysis, more free fatty acid will be produced, and we need more refining later. Hydrolysis reaction can be accelerated by high temperature, pressure, and water. For example, when we use a cooking oil in a deep fat frying of high moisture food. For example, when we fry fresh potatoes containing more than 80% moisture. So at high temperature and the presence of moisture in the food will cause hydrolysis of the triglycerides to produce free fatty acid. And over time, this free fatty acid will accumulate in the oil, and the result, it will reduce the smoking point of the oil, meaning that it will produce smokes in the oil when we use the oil in frying. Usually, the free fatty acid content in the range of 1 to 3% is tolerable, but when we have more than this, the oil will produce smoke easily when we use it in frying. The problem with generation of free fatty acid from hydrolysis is because the fatty acid in the free form is more susceptible to oxidation compared to when the fatty acid is esterified to the glycerol in the triglyceride molecule. So for example, the presence of short chain fatty acid in the milk will cause undesirable rancid flavor due to the hydrolytic rancidity. We have seen in the previous slide that generally hydrolysis reaction is undesirable for fat because it will generate free fatty acid, which can increase the cost of refining. But sometimes hydrolysis is desirable, for example in the production of cheese, especially during ripening process of a cheese, where certain type of mold is added to produce enzymes such as lipase, and this lipase would hydrolyze the fat in the cheese to produce and to give certain characteristic flavor to the cheese. And in some type of yogurt also, the hydrolysis of fat to a certain extent will produce a range of free fatty acid which provide a unique or characteristic flavor to the yogurt. But in general, in crude palm oil, between 3 to 5% of free fatty acid would be present, and this will be removed during refining, whether by using alkaline neutralization or by using physical refining by using steam distillation. Another example of when hydrolysis reaction of fat is intentionally done is in the production of fatty acid for the soap and oleochemical industries. So in this process, the fat is completely hydrolyzed to produce the free fatty acid, which serve as a raw material for production of soap and oleochemicals. So basically, with the application of heat and in the presence of water, the triglyceride molecule in the fat will be completely hydrolyzed to free fatty acid and also glycerol. Next, let's discuss about oxidation. Oxidation is usually undesirable reaction for fat. This is basically the reaction of the fat containing the unsaturated double bond, and it will react with the oxygen in the air, and it will produce a range of oxidized compound which can cause fat to become rancid. So this is a process of oxidative rancidity. So the unsaturated double bond in the fat will be oxidized by oxygen, and this reaction will be accelerated in the presence of high temperature, in the presence of pro-oxidant or trace metals such as copper and iron, and also in the presence of light. And this will produce oxidized product, for example, hydroperoxide and other smaller compounds such as aldehydes, ketones, and many others. There's a type of oxidation called auto-oxidation. This is basically the oxidation induced by air at room temperature, and this will occur as a radical chain process. What this means is that the free radicals will be formed during the reaction, and the free radicals are very unstable and reactive. So the reaction will go on to form more compound. So naturally, fat which contain high amount of free fatty acid in the triglycerides will be more prone to oxidation because the unsaturated double bond is very susceptible to the oxidation. And just like hydrolysis reaction, oxidation can be accelerated, or the rate of oxidation can be increased when we increase the temperature, when we increase the oxygen, and also in the presence of light, as well as the presence of pro-oxidants such as copper. Fat can also undergo polymerization reaction, for example, during deep fat frying. This is basically the reaction whereby small molecules such as aldehydes and ketones can combine to form a much larger molecules. The polymerization reaction can occur at a point of unsaturation on fatty acid chains, which are usually preceded by oxidation, or at the ester bond. As I mentioned earlier, polymerization reaction can occur during the deep fat frying of foods. Usually during frying, we operate at very high temperature, typically above 177 degrees Celsius. And also there's a presence of oxygen, which can accelerate oxidation process to produce a range of smaller compounds such as aldehydes, ketones, and hydrocarbons. And these compounds can combine and polymerize to produce a bigger polymer. Because polymer is high molecular weight compound, the polymerization will cause increase in the viscosity due to the formation of the big polymer. And if we allow this reaction to proceed, sooner or later it will result in formation of foam in the frying oil. So now let's look at the chemical changes and chemical reactions that can occur during deep fat frying. The process of deep fat frying is defined as a process of cooking involving the direct heat transfer of heat from the oil to the cold food. So as we know, deep fat frying is used widely in the food industry for various applications such as frying of French fried potatoes, seafoods, poultry, donuts, and many others. I'm sure you have experience cooking and frying using the oil. Probably you have seen a boiling action in the oil when you put the food inside the cooking oil. So what happens is basically when the food is placed in the hot oil, it is heated quickly to the point where water is vaporized and will produce steam, and this steam will cause the boiling action in the oil. But the boiling action also will increase the aeration of the oil. In other words, more air from the atmosphere will be incorporated into the oil during the frying, and this consequently will increase the oxidation of the oil, and more hydroperoxides will be formed in the oil. The peroxides are very unstable molecule, so they quickly decompose through fission and dehydration, and formation of these free radicals would form a variety of volatiles. This is called VDP, or volatiles decomposition products, and also non-volatile decomposition products, and VDP. The VDP are volatile molecules, so they are easily removed by the evolving steam in the hot oil. On the other hand, the NVDP, they are bigger polymers and maybe dimers and trimers, and they are not volatile, so they are not easily removed from the oil. Instead, they will be removed from the oil by absorption of the food being fried, or they will be deposited on the frying kettle, and this can be removed partly by using filtration. At the same time, some of the components, for example, the colored compound in the food, will be solubilized into the cooking oil. So during deep fat frying, we will observe some physical changes. For example, darkening of the frying oil. This usually happen when through non-enzymatic browning or Maillard reaction, especially when we have protein and also high amount of reducing sugars in the food. And of course, during deep fat frying, we will get chemical reaction in the form of oxidation. So when the temperature is high, the rate of oxidation also will increase, and the oxidation reaction in the frying oil will be accelerated also by the presence of pro-oxidants such as iron and also copper. So in order to minimize this oxidation reaction in the frying oil, we can add antioxidants such as BHA or BHT to minimize the process of oxidation. If the deep fat frying process is extended over quite a long time, then we can get a polymerization reaction. This polymerization reaction will produce polymers, and this will also increase the viscosity of the oil, and as a result we can get foaming and also gumming. To reduce this problem, we can add anti-foaming agent. For example, we can add methyl silicon at 0.5 to 2 ppm to reduce the foaming in the frying oil. Most food will contain some amount of water, so when we fry the food, the water will cause hydrolysis of the fat, and this would generate free fatty acid in the frying oil. So the rate of this hydrolysis would increase with more water in the food and with higher frying temperature, and the slower turnover means that we don't replace with the fresh oil as often as possible, and with increased amount of food being fried. So in this graph, it shows the free fatty acid development during deep fat frying. So we plot the percentage of free fatty acid on the y-axis here and hours of frying on the x-axis. So we have three curves here. 0 red means there is no food inside, or there is no potato, it's just oil. Low potato rate means that we have relatively small amount of potato, and high potato rate means we have high amount of potato. So we can see as we increase time of frying, the amount of free fatty acid produced in the oil also increases. But when there is no food in the oil, the formation of free fatty acid is not that much compared when we have high amount of potato in the food. Because when we have high amount of potato, more water is present, So this would cause more hydrolysis of the fat, especially at high temperature, compared to low potato rate. So the generation of free fatty acid with high load or high amount of high moisture food in the frying oil will produce more free fatty acid. And in this figure, it shows the development of foam during deep fat frying. So we plot the percentage of foam height on the y-axis as a function of hours of frying. So again, we have low potato rate, zero rate, and high potato rate. In general, as we increase the time of frying, we can see there is a general increase in the foam height for low potato rate as well as zero potato rate. For the high potato rate, high amount of potato in the frying oil, initially there is an increase in the foam height, but at one point, the amount of foam is actually lower compared to the low potato rate in the oil. So this probably due to the generation of more free fatty acid in the oil, and there is also the formation of maybe mono and diglycerides as a result of partial hydrolysis of the fat. And mono and diglycerides in this case can serve as an anti-foaming agent which can reduce the foaming height in the high potato rate oil. Okay, this diagram summarizes the changes during deep fat frying. So we have the food containing some moisture. We add the food into the oil, and the oil now is at a very high temperature, above 170 degrees Celsius. So very quickly, the water in the food now will flash off and vaporize in the form of steam. So this is when we get the boiling action in the oil, and some of the steam will escape from the oil into the atmosphere, but some of this would cause hydrolysis of the fat in the oil to produce free fatty acid and a mixture of diglycerides, maybe monoglyceride, glycerin, and other than steam, some other volatiles also will escape and vaporize from the oil into the atmosphere. The vigorous boiling reaction of steam in the oil would cause aeration of the oil, which will draw oxygen from the atmosphere into the oil, and this will cause oxidation of the triglycerides in the oil and produce hydroperoxides. And the hydroperoxides are very unstable and will go through other reactions such as fission to produce alcohols, aldehydes, and other compounds such as acids and also hydrocarbons. Colored compound also will be formed during frying due to the reaction such as non-enzymatic browning and also Maillard reaction due to the presence of protein component and reducing sugar in the food, which produce the the brown compound and cause and give color to the food. At the same time, other components in the food might be solubilized into the oil, and this we will be perhaps absorb some of them on the food surface itself. The hydroperoxide compound formed from the oxidation can produce various other compounds through various other reactions to produce, for example, ketones and other free radicals, dimers, trimers, epoxides, alcohols, and hydrocarbons. And these smaller compounds on extended frying would form polymeric compound through the polymerization reaction, and consequently this will also increase the viscosity of the oil. So as we can see during deep fat frying process, the combination of the moisture, the temperature, and also the presence of air would cause various physical and chemical changes to the fat. So what will happen if we use the frying oil again and again for a few times? So you can imagine more free fatty acid will be accumulated, more polymeric compound will be accumulated in the oil, and more solubilized compound will be also accumulated in the oil. So as a result, when we have more free fatty acid accumulated in the oil, it will reduce the smoke point of the oil, which means that the more you use the oil repeatedly, then the next time you use, you will see that the oil will start to produce smoke and also to start to produce foam, even at a lower temperature. So in other words, the quality of the oil will be reduced. Okay, this is another diagram which summarizes the changes during deep fat frying. So in this diagram, you can see starting from the induction period, this is where the period, a short period where the cooking oil is still quite stable. Then we start to get a peroxide formation due to the oxidation of the oil. Then we can see this is a peroxide. We can see that initially the formation of peroxide is quite high and very fast, up to a point when the peroxide start to decompose and produce various other compounds. So the peroxides in this case will start to decrease. And as we continue the cooking or the frying process, the small molecular weight compound formed through the peroxides would polymerize and form a bigger polymer. And as we get more polymeric compound to form during frying, the viscosity of the oil will start to increase gradually. So this is where we get the polymerization stage. So we have peroxide formation, peroxide decomposition, and we can get to a point where we get a polymerization with a corresponding increase in the viscosity. And we have oxygen in the oil, and this oxygen can be pulled in or incorporated into the oil due to the vigorous boiling reaction of the steam in the cooking oil. So this shows the amount of oxygen in the oil here, and the amount of oxygen absorbed in the oil, which increase as a function of frying time.